Well, hi everyone. I have a more technical video for you today, but I think you'll all find it to be very interesting. So what we're talking about here today is how do you really optimize the length of piling for a pile-supported bridge during the design phase? How do you really decide how far the pile are going to penetrate into the subsurface soil or rock in order to determine planned order lengths for the contractor? Well, we'll go through that today. I think my company's developed a couple of innovative approaches, and certainly I think it's been very effective in fine-tuning or optimizing required pile lengths so that there's no sudden surprises in the field where you suddenly have to order more piling or you're going to have excess cutoffs when you can't drive the pile as far as you thought. So as a reminder, this is what we're talking about. This is a typical PDA test. This job is on the US 69 Tollway project in Overland Park, Kansas. You can see they've got clay fill over shale bedrock, and in this case they actually pre-bored to get sufficient pile length below the ground surface. That's to provide a sufficient lateral support for the piling. Pile buck there marking the set, so basically he's marking every 5 blows, and that's an important parameter for our subsequent analysis and for verification for the other piling that are driven that aren't subject to dynamic pile testing. So what we did, as I mentioned, we've developed a couple of innovative approaches. First of all, we took our data set. So we've tested hundreds of bridge projects, thousands of piling, concentrated primarily in Kansas and Missouri, but we've done testing all over the country. And we realized that on job after job, we'd have a situation where a consultant design project, in most cases, the piling were either ended up way too short or way too long relative to what was indicated in the plans. And we would see this on a job, and then maybe 6 months, 18 months later on a nearby bridge, the exact same thing would happen again. And we started asking ourselves, aren't these people communicating these results and getting after action report about what happened on this job so they can use that information on the next job? And we found that, you had different consultants involved with various projects. You had different entities, whether they are county in some cases or the state, and it was very difficult for people to lay their hands on past reports and provide it to the designer for a new bridge. And we realized we were setting on thousands of PDA tests where we had information about the hammer, the pile, the design requirements, the tested capacity, the performance of the hammer in terms of hammer ram stroke. That's how far the piston rises between blows on the diesel hammer, the pile set, how far it penetrates into the ground after a given number of blows. So we had all this information, and we realized, we have, as people who perform dynamic pile testing, good institutional knowledge about what it takes to drive a pile to a given capacity in a given area of, say, Kansas or Missouri. But the designers often don't have that information available, or the owner of the project may not have that information. So we decided to create a data analytics suite by creating a highly curated data set of our past project information in terms of pile requirements and pile testing performance and hammer performance. And we started seeing really good correlations. And these correlations match what we already knew based on years and years of testing experience. But what was great about this is that other people could independently access this information and come up with their own conclusions, even if they didn't possess all that institutional knowledge. It was an independent way of getting a handle on what they could expect on their pile-supported bridge project. And the other aspect that we employed to optimize pile lengths was employing geophysics. We did a series of case studies throughout Kansas in 2022 where we went back to jobs that had been built already, where we had previously done the pile testing, and did surface geophysics to see if there were indications of certain compression wave velocity where the piles ended up being driven to, so that we could say, hey, for a given type of subsurface material, you would expect the pile to go into a layer that has this compression wave velocity to develop the required capacity. And so I'll cover more about both of these here as we go forward. So this figure, this is from our data analytics package. And by the way, we initially created this for ourselves, but Kansas DOT has subscribed for the last several years to this data analytics package. So they're using it now to optimize their design and assist with construction oversight for these pile-supported bridge projects throughout the state of Kansas. And it's been quite effective for them. So we're going to be talking more about Sedgwick County here. We have 12 bridge projects in Sedgwick County that's currently in the data set. So when we talk about data analytics, there are three main types. First, you have descriptive analytics. What's happened? What's a typical pile length for a given capacity at a given location? That's merely descriptive. Diagnostics would be identifying where piling were either much longer or shorter than planned and determining a root cause for such a situation. And then finally, you have predictive analytics. That is to take a given set of conditions, a certain site, certain pile size and capacity requirement, and being able to predict the likely outcome for the installation of that pile. So all these things we've brought together, and I've got a specific case study where we utilize both of these tool sets to optimize pile length to save tens of thousands of dollars in piles that were ordered for a particular project. So I'll go over that here in some detail here. So we can produce plots like this in our analytics package where you have total actual pile length versus pile plan length. And you can see there's a wide amount of scatter. And we can go back and drill down on these areas where the pile were either much shorter or much longer than planned and start identifying what is the commonality for these jobs and identify root causes to inform the design and installation of these piles on subsequent projects. So this is another useful graphic that we can produce in our data analytics package where you have pile depth versus bedrock depth. So the orange is the max pile depth and the blue is the average depth to bedrock. So you can see in general what the difference is between those two plots is what the typical penetration of the piling into bedrock was for that job. And this is very useful for getting an idea of how long the pile need to be at a given project. And it's good too to generate plots like this where historically what have been the average required capacity by given pile section size and type. So you can see we have H-pile sections as well as pipe pile sections. We could also do things like where we've got restrike data in our data sets to plot capacity over time such that it would be possible to have your required capacity correspond to a point farther out in time so that you don't have to drive the piling as long. So as long as you drive a pile to a capacity that's going to plot on the line, you can anticipate at some future point that you'll get your required capacity. So these are quite useful. These are what's called pile setup curves. And this is related to time-dependent capacity increases due to dissipation of excess pore water pressures, primarily in clay soils surrounding the pile. So I mentioned a specific case history. So just as we had developed these data sets and just after we had done our geophysics correlation studies, we were retained by King Construction in Kansas to provide the dynamic pile testing for a pile-supported bridge in the city of Wichita. And on this project, there were a total of 236 pile and over 14,000 lineal feet of piling. So average individual pile length was 60 feet. And one of the things we noticed right off the bat was, hey, we don't think that the pile is going to penetrate this far into the shale bedrock. And this is a particular problem in this region in that if you're driving pile, say, through clay to a hard bedrock layer, such as a limestone, and that limestone layer maybe, say, 30 feet, you can be pretty well assured that you can take an H-pile and drive it to end bearing into that hard layer, and you know roughly how long that pile needs to be. In the case of what they call intermediate geomaterial, where it's better strength-wise than a soil, but weaker than a hard rock, is what you have with these weathered shale formations, it can be quite difficult unless you have extensive testing and construction experience into determining what the required pile length should be. And that means, how far is the pile going to penetrate below the top of the bedrock contact, the weathered bedrock contact. Again, this is a still photo from that earlier segment where I showed the pile driving and just shows the exposed shale surface. And shale is typically highly weathered at the upper portion, and then it grades into harder and harder material with depth. Of course, this is a sedimentary rock, and so you typically have horizontal bedding planes that are visible. And even in the case where the upper profile is pretty much soil, the soil can retain some semblance of that rock structure. So how did these materials form? Well, in the Permian period, this was around 290 million years ago, about from 250 to 290 million years ago, there was a huge inland ocean, and these are ocean deposits. This is the distribution of what's called the Wellington Shale Formation. It covers a wide area of Kansas into Oklahoma and a corner of Texas. So these are shallow ocean deposits. If you look to the right, that's your shore. You could have coal in the marshy areas. Then you have sandstone that form from the sand that were formerly beaches. And then you have the clay particles that stay in suspension longer. They travel farther offshore, and they're deposited and over time compressed to form shale. And then in the deeper part, farther distance offshore, you have limestone, so chemical precipitation of calcium carbonate. And these are called facies. And facies in geology is the character of a rock expressed by its formation, composition, and fossil content. And you can have these formations be cyclical because the ocean level can rise or recede. And so in a given area where you used to have, say, limestone, if you have the ocean recede, you could get shale or sandstone deposited on top of it. And this is what you get throughout the Midwest and other parts of the country where you have these layers of shale, limestone, shale, coal, and so on. And that's called a cyclothem, which is just a series of sedimentary rock layers that repeat vertically. We did our data analytics as well as geophysics at this particular site in Wichita, and we recommended significantly less pile order lengths. It saved over 10% on pile length versus plan, and I understand that resulted in a savings of over $60,000 on this project, which was significant because the owner of this project doesn't pay for cutoffs. So if you have a set of plans that say, hey, you've got to furnish 14,000 lineal feet of piling, and you don't use it all, the contractor's stuck with having paid for it in the first place and then having to cut it off and haul it off. So I'll go through in a little more detail how this actually shook out. But as I mentioned, we went through our data analytics. We could do things like hover over Sedgwick County, and we see the typical penetration in the bedrock ranges from 3 to 43 feet with an average of 16 feet. So that's a good starting point. As I mentioned, I had a project in the same area, I think within a mile or two of this particular project years ago, where the designer anticipated 50 feet of penetration into the shale bedrock, which is utterly impossible. But if they had a tool like this, they could see that 50 foot of penetration would be at the extreme outlier for this situation. Then we looked at average pile length in this county. We got 52.6 feet and average capacity, and we could select different pile sizes. So this particular project, the pile sections were HP 12 by 53, and for Sedgwick County, the average capacity is 333.8 kips. A kip is 1,000 pounds. And we could do things like this: pile depth versus total pile capacity for a given pile hammer. And we've got this gray areas, which is within a half a standard deviation of the mean. And so if you're designing pile, initially you might want to say, hey, let's pick a pile length and capacity that falls within this gray band. Then we could do things like generate a plot of hammer ram stroke versus total pile capacity to give an idea of what the hammer stroke should be. So in this case, the required capacity for this case study was 268 kips, which would be about a 7.5 foot stroke. And then for that same capacity, the pile set per blow is about 0.25 inches per blow. So 1.25 inch per 5 blows. We typically compute set in 5 blow increments in this region. So on to our seismic refraction study. We went to 18 sites in total. Geometrics sponsored this for us by providing a set of equipment. We've subsequently purchased this equipment, so we own it, and we're able to do this on new projects. So we compiled profiles of the compression wave velocity of the subsurface soil and rock and correlated that with pile penetration depths. And these are my two youngest boys. I put them to work. This is rather physical work where you have to lay out sensors called geophones. They're accelerometers. You lay them out with a certain spacing along the line of interest. You have a computer that's set up, connects everything. You can see this plate in the foreground. To impart energy into the ground, we strike the plate with a sledgehammer, say a 10 or 20 pound sledgehammer. Now for this case study in Wichita, we selected lines for our surveys. We used Google Earth to get an idea of how well we could lay these lines out given constraints of physical access, vegetation, and that sort of thing. And from our case studies, we found that piles typically ended up where where the pile tip was, the compression wave velocity of that material was on the order of around 6,000 to 7,000 feet per second. So for this project, we determined that the probable tip elevation for the piling was elevation 1250, which corresponded to a compression wave velocity of 6,500 to 6,800 feet per second. This blue area, which shows apparent high velocity, that's just the footing for the pier at this location, the reinforced concrete footing. And then on abutment 2, similar fashion, we determined the probable pile tip elevation was 1,252 feet, corresponding to a compression wave velocity, again, between 6,500 and 6,800 feet per second. So we made these predictions. The contractor ordered 10% less piling relative to plan, and we went out and performed the PDA testing, one pile for each substructure. So there were 4 piers and 2 abutments. And I'll just show you a quick video of us testing one of these piles at a pier location. And this is how it turned out. I just picked an excerpt from a report for abutment 2. So as you'll recall from the geophysics survey that we performed, as well as our correlation to our piling data set from our PileTrac application, we estimated pile tip elevation to be elevation 1,252 feet, and actual pile tip elevation turned out to be just 1.2 feet lower. So that's very, very good correlation. And you can see the bedrock starts where it's weathered. The contact really between soil and weathered shale is at elevation 1260. So we had about 8 or 9 feet of penetration into the shale formation. And in terms of hammer performance, we ended up with a 7.5 foot stroke, a set of 1 inch and 5 blows to get our minimum 268 kip capacity for the piling. So let's go back and look at our data set. So we selected all the data that was collected using a D1632 hammer, which was the hammer used on this Amidon project. And then we selected HP 12x53. And so we go over to look at 268 kips. That corresponds to a 7.5 foot stroke, which is exactly how it shook out. So this data analytics package can be used, I think in some cases, to be more accurate than a wave equation analysis. That is to model what the pile driving characteristics are before you actually go out in the field and drive the pile. Now let's look at the pile set. For 268 kips, we're about 0.25 inches per blow, and we ended up at 1 inch and 5. So the prediction is 1 1/4, and we ended up with 1 inch and 5. So again, very, very close, which is really interesting because it comes out of the actual data. And so sometimes contractors aren't sure what kind of hammer they need to drive a pile to a certain capacity. When you select a hammer, you don't want to have too many blows because it's very time consuming to install the pile if you have to have too many blows per given amount of penetration. And you don't want to have too big a hammer because then it's just too much energy, you risk damaging the pile. So let's go back and look how this job actually turned out. Let's look at the central area of this table where we have actual average pile length, and we got 54 feet, maximum's 55. Our predicted was 55.5. And then next one predicted was 32. The range was about 31 to 35 and so on. We were within a foot or two of actual versus predicted, which is very, very good. So I mentioned you can use this data to identify root causes for why piling in a given region may go deeper than planned or shallower than planned. And one of the root causes that we identified is related to the geotechnical investigation that's performed in the shale formation. The soil borings are typically advanced using a hollow stem auger. So this is just twisted into the ground. It has a center plug. You remove the center plug and you attach a split spoon sampler, and it's driven into the ground, and you record the number of blows per foot. So for hard shale, you would have in excess of 50 blows per foot, often times 50 blows for some number of inches of penetration. So what we've noticed though is that some drillers are very, very good at actually able to core through highly weathered shale. And other drillers burn through quite hard shale before they start doing SPT sampling. So a lot of designers will recommend a certain pile penetration, whether it's 5 feet or 10 feet, once you encounter a 50 blow per foot material. Well, if you've burned through 10 feet of good material that would have been 50 blow per foot, but you augered through it without sampling, you're going to miss the fact that your piling is actually going to take up much higher in elevation. So another root cause issue that we've identified is we find that contractors and certainly people like us who perform routinely dynamic pile testing on projects have a very good internalized knowledge about how long a pile needs to be and what size hammer you need to develop a certain required capacity, and also what typical penetration is going to occur in these weathered shale formations. And because of the increasingly compartmentalized nature of pile design and construction on bridge projects, you may have one company that's the geotechnical firm that does the soil drilling and sampling and makes recommendations for pile lengths. And then you have a structural engineer who takes that recommendation and determines the detailed requirements for the piling. And then you have the owner issue a set of plans with this information, and then the contractor has to build the job, and then they retain somebody like me to do the testing. And unfortunately, more often than not these days, as soon as we get the plans, we'll say, yeah, we can do the pile testing for you, but these pile lengths are wrong. You're not going to either go that far or you need to go longer with the piling. So I think more designers should reach out to contractors and also, in particular, people with experience in dynamic pile testing in a given region to get feedback, to basically do constructability review for their planned piling project. Just do a sanity check. Are these pile lengths reasonable? Are these penetration depths into the weathered shale, in this case, reasonable? You know, how much extra margin should we have? And if you want to take it to the next level, if you've got somebody like us who's utilizing an extensive data set that has tremendous amount of historical information, that's even better. And then we could layer that with geophysical surveys to fine-tune our piling recommendations. So this is a powerful suite of applications that can be brought to bear to optimize pile length for a pile-supported bridge project. And we offer our services if you are a contractor or project owner that has access to a few dozen data sets, PDA reports with results of testing one or more piling. We find that a data set of 50 PDA tests, or 50 bridges in particular, is fully effective in making these correlations for a given region of a location where piling would be installed. And so reach out to me. This is my email. If you have data sets that you would like to see incorporated into the PileTrac service, and you could subscribe to that, or if you've got the need to optimize piling and where we can employ geophysics, so let me know on that as well. But again, I'm really pleased that I think this is rather innovative, and I don't know of anyone else who are using these tools to this degree to optimize pile length prior to construction. So with that, I want to send a shout out to those of you who have contributed to buy me a coffee. That's an excellent way to support the channel. I also want to thank those of you who are channel members. I've had several channel members who have been on board for over a year now, and I tend to have a lot more interaction with channel members, and they also get to preview videos, my typical releases, a day or two more in advance. And also I want to send a shout out to those of you who provided super thanks. That's another great way to support the channel. So I'll continue to do detailed videos like this, various aspects of pile design, installation, and testing, so please stay tuned for future videos.